Welcome back, Patriots. I am Mr. Love, also known as the Math Patriot, bringing you another fun and exciting lesson in the world of high school geometry. I apologize for being out of touch for a while. We had some technical difficulties getting some new technology in the classroom, and I wasn't able to record for a while. But we're starting back up and getting on to Unit 6 today. I am not recording live in front of a class. Today I'm doing this actually at my office at home at about 9 o'clock p.m. on a Sunday night. Did this lesson live with my class before the Thanksgiving break and wanted to get this video posted before the everybody comes back. That way anybody who wasn't there can get caught up. So we're starting off on a new units. We're starting off on polygons and specifically parallelograms towards the end of the lesson today. Now, just remember where we started off with in this whole geometry process. We started off with taking the very basics of geometry. We talked about the three undefined terms. We got our point, we've got our line, and we've got our plane that extends on and on in all directions. Solid, well, not solid, but a flat surface that has infinite width, infinite length, and no thickness. All three of those were our undefined terms. We took those and we started combining them together and cutting them and slicing them and dicing them, and we ended up getting, things like line segments. We ended up getting rays. We combined two rays together and we got angles. Then we took the idea of two things being parallel, cut it across the transversal, got all these different angle relationships inside of there, and now we're going to keep on building up. Then we kept on building up and we eventually created triangles. We learned all about isosceles and equilateral triangles, all the different relationships inside of those, all the way down to those dreaded 4 points, the incenter, circumcenter, orthocenter, and centroid. And we've been doing this whole thing of essentially taking those original three undefined terms and building up bigger and badder shapes. And we're going to continue doing that by continuing on to polygons and quadrilaterals for the majority of this unit. So that's what we're going to be doing. The reason it's important to realize that we're essentially taking triangles and building polygons out of them is because we're then able to leverage all of the things that we learned about these pesky little triangles in the last unit and apply those over into our polygons and parallelograms and use all that information in order to build up bigger and badder shapes. So first off, what is a polygon? A polygon is a closed figure formed by a finite number of coplanar segments called sides. Now, the word closed there is actually very important because we couldn't do something like this. This would not be considered a polygon because we've got this big open area right there. Now, if we were to even draw in other sides and close that off, then yes, that would be a polygon. Now, finite number of sides, basically, they have to be countable. That kind of prevents us from getting into the idea of a circle is an infinite number of sides. So circles don't work in this whatsoever. And they have to be coplanar because we couldn't, take a line up on a three-dimensional axis here. That's not going to work. And all these straight sides or segments that are coplanar here, they're forming the polygon, are going to be called our sides. Now, there are two basic overall types of polygons, concave and convex. Convex is where all of the vertices flex generally in an outward direction. Concave is where they're going to dip in this sort of fashion. Anytime that it kind of caves in, it's concave. You'll notice this one I drew up here has got this guy right there, makes it a concave polygon. Next up, three other words, equilateral, equiangular, and regular. Now, for equilateral, we talked about equilateral back with our triangles, and it just meant that all sides are congruent. We also talked about equiangular very, very briefly in that unit, and what we decided there was that equilateral for triangles always implies equiangular, and equiangular always implies equilateral. Those two are essentially synonymous. Now, for a polygon, that is not true, or for bigger order polygons. All you have to do is look at quadrilaterals to see that that's not true in general, because it is possible for us to have a four-sided shape in which all four angles are equal, yet it's not equilateral. Because we got equiangular, all four right angles, however, not equilateral. We could also do the exact same thing and have all four sides be the same, yet all four angles are not the same. In this case, we have a rhombus versus a rectangle. So For higher order polygons, equilateral and equiangular are not exactly the same thing. However, if we do have a polygon that is both equilateral and equiangular, we call that a regular polygon. As you can see in this pentagon down here, all the angles are the same, all the sides the same, therefore it's regular. For our quadrilaterals up here, we have a square is our regular quadrilateral. By the way, as far as I know, and I could be wrong, but as far as I know, the only two shapes or polygons that have a special name for a regular polygon is a triangle and a quadrilateral. The regular triangle being equilateral, and then the regular quadrilateral being a square. The rest of them are just called regular hexagon, regular octagon, etc. Now, as we go on to that, it is important for us to be able to know all of the different sides, or all the different names of polygons with the various sides. Many of these you would probably be familiar with. 3 is triangle, 4 is quadrilateral, 5 is pentagon, hexagon, heptagon. By the way, some people will use septagon here. I know what you're talking about if you say septagon for a 7-sided polygon. However, let's make sure you're doing it right when using the H there, heptagon. 8 is octagon, 9 is nonagon, 10 is decagon. 11 is one that's not commonly used, but for the purpose of our class, we're going to go ahead and use it. That is a hendecagon. 12 is a dodecagon. For whatever reason, the dodecagon is more common than the hendecagon. And at one point in my life, I had a little bit too much time on my hands, and I actually memorized the names of all of the polygons up through 100. I do not wish that on you guys, therefore I'm not going to make you do it. Anytime we get beyond 12, we are just going to call it an n-gon, where m is a variable for the number of sides. So if I ever ask you what is the name of a 23-sided polygon, let me see if I can spell polygon correctly. I'm a math teacher, not an English teacher. Polygon. All right. A 23-sided polygon is a 23gon. So what's the name of a 100-sided figure? You could say centagon, or you could just say 100gon. Either one works for me. So make sure you know all these, and the rest of them, bigger than that, we're just going on with the name or the number. Now, using the variable n here as the number of sides is actually going to be very important, especially as we get into some of our polygon properties in the next few pages here. Now, also a little bit of vocabulary. A diagonal is a segment that connects any two non-consecutive vertices. Non-consecutive is important here because here P and T are consecutive, and the segment that connects those is the side of the polygon, not a diagonal. Same logic with PQ. Okay, that is also a side. Now, PS and PR are both diagonals. Now, I could have drawn diagonals from Q over to QT and QS, etc., but for the purpose of the example, I just needed all the ones from P. Now, let's go ahead and talk about the measures of polygons. We already know that there are 180 degrees if I add up the interior angles of a triangle. Now, the question is there a pattern for the sum of the interior angles as I go up in the number of sides of a polygon? Well, here's what I want you to notice. If I take a single vertex of each of these polygons and draw all the diagonals that come out of that vertex. Now notice I didn't say all the diagonals in the entire shape, because I could have drawn this diagonal here. That's not what I want to do. I'm going to draw all the diagonals from this one that I've labeled in green. What you'll notice is that as I add on sides, there are actually more and more diagonals going on, which makes sense because as I'm adding on extra vertices, then I have more potential for more diagonals. The triangle has no diagonals, quadrilateral has 1, pentagon has 2, hexagon has 3, and so on. Now you'll also notice that as I am doing that, I am dividing the polygon into sets of, or a series of triangles. And the number of triangles actually goes up as I'm adding on more sides. See, a triangle only has one internal triangle. The quadrilateral has 2. The pentagon has 3. The hexagon has 4. Now, you'll notice on here that the n value here, n equals 3, and my triangle number is 1. Here n is 4, and I have 2 triangles. Here n is 5, and my number of triangles is 3. Here n is 6, and my number of triangles is 4. In every single case, the number of triangles is exactly 2 less than the number of sides. Now, what does that do for me? Well, I was talking about finding the sums of the interior angles. Well, this one triangle we know has 180 degrees in it. We also know that this triangle here, let me go ahead and erase these squiggles, this triangle on bottom has 180 degrees, and that triangle has 180 degrees. If I add up 180 plus 180, that means that a quadrilateral will have 360 degrees in it. I could do the exact same thing on this one. 180 plus 180 plus 80 is 540. I can't write today either. 540 degrees. Same thing for my hexagon. I've got 4 triangles, so 180 times 4 is 720 degrees. Now what that means is I am seeing a pattern. It looks like I take the number of sides and subtract 2 to get the number of triangles, then take that and multiply by 180, and I get the sum of the interior angles. So that's all this chart is doing down here. I've got number of sides, number of triangles, then my number of sides is n, number of triangles is n minus 2. Therefore, the sum of the angle measures, or the interior angle measures, is n minus 2 times 180. Now, that's not saying anything about the measure of each individual angle. All it says is that the sum of the angles is 180 degrees. Now, there is something special we can do there. For a regular polygon, if I want to know the measure of each angle, then all I'm going to do is take this formula and divide it by the number of angles. Well, if I have n sides, I also have n angles. So each angle here is going to be n minus 2 times 180, all divided by n. And you'll see that formula come back up here in a couple of examples from now. All right, here is that exact same idea, just written out in theorem form. The sum of interior angle measures of an n-sided convex polygon is n minus 2 times 180. Same idea here. We have five sides, so we just do 5 minus 2 times 180 gives me 540. All right, a convex polygon has 13 sides. Now, let's see if we can refer back to earlier. What would I call a 13-sided polygon? I'll give you a second to think about that. That is a 13gon. Yes, we just use the number because it's bigger than 12. Find the sum of the measures of the interior angles. Well, it's going to be n minus 2 times 180, where 13 is n. So we got 13 minus 2 times 180. So that's 11 times 180. And, oh, I don't have a calculator handy. Oh boy, that'll be the same thing as 10 times 180 plus 180. So that's 1800 plus 180, which is 1980. 1980 degrees. Come to think, I better grab a calculator because I've got some more difficult problems coming up here in a minute. I'll just use the one on my computer that's in front of me. Okay. Measure of an interior angle of a regular polygon is 120. Find the number of sides. Now, notice it says the measure of one interior angle of a regular polygon. Regular implies equiangular, and that's where we're going to come up with that formula from earlier. Actually, I take it back. I made a mistake on that. I shouldn't have said regular. I should have said equiangular on this. So anytime I have an equiangular polygon, each angle is n minus 2 times 180, all divided by n. So let's take that formula, n minus 2 times 180, all divided by n, and that equals 120 degrees. Now we've got to figure out how to solve this thing for n. Well, I know I have a phrase I use in class a lot, fractions are our friends, but that doesn't mean I have to like to hang out with them. I'm going to try and get rid of that as quickly as possible. I'm going to go ahead and multiply both sides by n, which is going to make those cancel out, leaving me with, I'm going to go ahead and distribute this up here as well. 180n minus 360 is equal to 120n. Now it looks like I need to isolate the n's on one side, so I'm going to subtract 180n from both sides, leaving me with negative 60n. divide both sides, going to give me 6 is equal to n. So find the number of sides. It's a 6-sided polygon, therefore that is a hexagon. All right, find the value of x. Now it looks like I've got 1, 2, 3, 4, 5 angles, making this a pentagon. So here n is 5. And it looks like all of my expressions are the interior angles of that pentagon. So I'm going to start by finding the sum of the interior angles of the pentagon. So I'm just going to do 5 minus 2 times 180, which I've already done several times in this lesson. That's going to come up to 540 degrees. Excuse me. Now I'm going to take all of these expressions and combine like terms. So I've got 4x plus 5x is 9x, makes 15x, that makes 19x, that makes 26x. And now we've got 5 minus 5 cancels out, so we've got 10 plus 10 is 20, so plus 20, and that equals 540. Let's go ahead and start simplifying this down. 26x equals, subtract 20 on both sides, gives me 520. I said it right, I wrote it wrong. And then 520 divided by 26, I should be able to do that in my head, but I can't. That is 20. Just divided through by 26. All right, exterior angles. Now, it kind of makes sense on some level to think that the more angles I add in, then as I'm drawing my exterior angles, I should be getting a greater sum out here on the outside. But here's the problem. Every time that I add on more angles, my interior angles in general tend to get bigger. You'll notice that on average, here the angles of my hexagon are larger than the angles of my triangle. So even though I have more exterior angles, since the interior angles are larger, then the exterior angles on average get smaller. So you'll notice if I add these up, 120 plus 100 plus 140, the sum of the exterior angles is 360 degrees. You'll also notice that if I add up all of these exterior angles, my sum is still 360 degrees. So that's it. It doesn't matter how many there are, you're going to have the sum of the exterior angles is always 360 degrees. So exterior angle sum theorem is that the sum of the exterior angle measures of a convex polygon, one at each vertex, is 360. End of story. So find the sum of the measures of the exterior angles, one at each vertex of a convex, and I don't care what that number is right there. The answer is 360 degrees. That could have been a billion. I don't care. 360 degrees when I'm looking for the sum of the measures of the exterior angles, one at each vertex. Example 5 here. Find the measure of each exterior angle of a regular hexagon. Notice this one says each of a regular. Regular implies equiangular. Now on a hexagon, n equals 6. So the sum is 360. So all I have to do is divide by how many there are, which is 6. Therefore, it is 60 degrees. Simple enough. Okay, found the value of x in the diagram. Looks like all of these are exterior angles, one at each vertex. So I'm just going to be adding and combining like terms and then setting them equal to 360. So 4x plus 6x is 10x, 15x, 20x, 22x, 25x. And now 4 plus 2 is 6, plus 3 is 9, minus 4 is 5, plus 5 is 10. And that equals 360. So 25x equals, subtract 10 on both sides, gives me 350. And now when I divide that through by 25, it gives me x equals, and if I'm right, that should be 16. Let me use my handy dandy calculator. Nope, I was off. That is 14. x is 14. 350 divided by 25 is 14. I should have known that. That's quarters. Oh well. Okay, now down to quadrilaterals. We're going to be spending the rest of this unit talking entirely about quadrilaterals. We're going to talk about parallelograms today. That's going to be our foundation for several other shapes we're going to be covering in the next lesson. So first off, a parallelogram is a quadrilateral with both pairs of opposite sides that are parallel. So here BC is parallel to AD and DC is parallel to AB. Our symbol is the parallelogram symbol, which just as always in geometry looks exactly like what we're describing. So several properties of parallelograms. First off, opposite sides are always congruent. So here JK is congruent to ML and also JM congruent to KL. Think of this as a rectangle that's gotten lazy and fallen over, and then it all just makes sense. Those two are equal, those two are equal. Also, opposite angles are congruent. So here M and K are congruent and J and L are congruent. Also, any pair of consecutive angles is supplementary. So here, angle K and angle L, or y degrees and x degrees, have to add to a 180. Now, we also know that these two are equal. So if this is y, that's y. This x and this y adds to 180. Those two add to 180. Those two add to 180. And when you think about it, this actually makes a lot of sense because we said that these sides here, JK and ML, are parallel. If I cut that by a transversal, then these two angles here, this y and this x, are consecutive interior angles. Therefore, they have to be supplementary. So this fits in exactly with our transversal properties that we learned back in Unit 3. Now, also, if a parallelogram has one right angle, then it has 4 right angles. This is actually pretty easy to see as well because, well, we just talked about our angle properties here. If J is 90, then L, being congruent to it, also has to be 90. And we know that consecutive angles in a parallelogram must be supplementary. So if this is 90, then that must also be 90, and then exact same logic gets you that K is a right angle. So one right angle means they are all right angles, provided that you have a parallelogram to start with. All right, let's do a few examples here. If ABCD is a parallelogram, find the value of each variable. Well, I know that opposite sides are congruent, so 2A has got to equal 34. Dividing through gives me A equals 17. We also know that opposite angles are equal, so angle A is congruent to angle C. Therefore, 8B is equal to 112. Divide 112 by 8, and we get 14. Example 8. If the diagram is a parallelogram, find the value of each variable. Well, I know that here 2y and 5x are equal, but I can't really do anything with that because of the fact that I would have two variables in the same equation. Now, if I had tried to essentially get rid of this diagonal here, I know that this whole greater angle, 60 plus 55, is 115 degrees. And I know that these two are supplementary. So 115 plus 5x is equal to 180. Now our solving steps here, subtract 115, 5x equals 65. Divide through, that gives me x is equal to 13. Now, I'm going to do the exact same thing with the y. 115 plus 2y is equal to 5x, equal to 180. So 2y is equal to 65. Therefore, y is equal to 32 and a half. All right, diagonals of parallelograms. If a quadrilateral is a parallelogram, then its diagonals bisect each other, which means that here P is a midpoint of both DB and of AC. So we know that AD is congruent to, AP is congruent to PC, and we know that PB is congruent to PD. Notice we're not saying that the two diagonals are equal to each other, or that all 4 sections of the diagonals are equal to each other. Just that these two are equal and those two are equal. Okay, so they bisect one another. Also, we know that each diagonal separates the parallelogram into two congruent triangles. Again, that's pretty easy to see. We already knew that opposite sides are parallel to each other, and then if we draw a diagonal across, then we have a side, or have a third side of each triangle, and we get the reflexive property that BD is congruent to itself. Therefore, I've got side-side-side congruence for these two triangles. So the two triangles are congruent. All right, let's find our values of x and y. Here I know that E, since it's a parallelogram, it gives me that with this symbol here, that point E is a midpoint of both AC and DB. Therefore, 4y has got to equal 18, and 6x has got to equal 24. So we divide through. 18 divided by 4 gives me 4.5. And 24 divided by 6 is 4. So 4.5 and 4. All right, number 10, find x, y, and z. Well, let's see what we got here. Looks like our diagonals, P is going to be a midpoint, so 2y minus 5 has got to equal y plus 4, because those two are equal to each other. So subtract y on both sides gives me y, add 5 gives me y equals 9. Now for the x's, it looks like my opposite sides are congruent here. So 5x is equal to 27. Then we're going to divide through, and I can't do that one in my head. That gives me 5.4. Let me double check that. I say it. Yep, 5.4. And now I've got to decide how to find my z value. Now there's a couple ways of looking at this. First off, I know that these two sides here are parallel. Therefore, my transversal line QS means that my alternate interior angles are congruent. I could have also looked at it as the two congruent triangles that were formed by diagonal QS, and those two angles are equal. Either way it works. We've got that 3z is equal to 33, therefore z is equal to 11. All right, now find the coordinates of the intersection of the diagonals of parallelogram ABCD with the given vertices. Now, here's where just knowing a little bit about your properties can actually go a long way with having you do a lot less work. Now, I could go through and plot all my different points. I have no idea where they are. I just put dots on that thing. I could plot all of them, then go through, find this point, find point. Here's the thing, though. We always name around the outside, which means that A and B have to be consecutive angles. So that in particular means that A and C are opposite. So a diagonal will go from A to C. So all I have to do is find the midpoint of segment AC, and boom, that's the intersection of the diagonals, because I know that that midpoint is right where those two diagonals meet. So all I got to do is do my midpoint formula, which is x1 plus x2 all divided by 2, y1 plus y2 all divided by 2. And I'm going to do that with points A and C. So my midpoint occurs at x1 is 3 plus x2 is 3 all over 2. And then y1 is 6 plus y2, which is negative 2 all over 2. So my midpoint occurs at 3 plus 3 is 6 divided by 2 is 3. 6 minus 2 is 4 divided by 2 is 2. So the intersection of my diagonals happens at point 3, 2. All right, example 12. Find the coordinates of the intersections of the diagonals of ABCD with the given vertices. Same idea. I'm just going to take my diagonal, or my opposite corners. In this case, I'll use B and D. I'll find my midpoint. So I've got x1 is 2 plus x1 is negative 7, all divided by 2. y1 is 3 plus negative 2, all divided by 2. Midpoint comes in 2 plus negative 7 is negative 5, divided by 2 is negative 2.5. 3 plus negative 2 is 1, divided by 2 is 0.5, and that's where my diagonals intersect each other. So that's it. If you have any questions, feel free to contact me in class. We can make an appointment for tutorials, whatever you need. And as always, stay patriotic. And then I say that, and I wasn't ready to cut the video. Ha, there we go. Stay patriotic.